So now we're going to look at data analytics with SNOMED. And it's, of course, we're going to touch on some of the things that we have already covered today. And hopefully you'll get a bit elaborated on some of the techniques here. So I'm going to give you an introduction to the features of SNOMED CT that may be utilized for data analytics. Then I'm going to talk about a range of data analytics techniques, followed by an elaboration on specific data analytics tasks. And finally, I'll introduce you to expression constraint, which is a computable language used to query SNOMED CT. So we'll see how far we come with that. So let's consider what we mean by data analytics in the healthcare space. Data analytics can broadly be defined as the discovery and communication of meaningful patterns in data. So it's all about extracting useful information from healthcare data and applying this to describe and predict and to improve performance. So whether that's clinical performance or its service delivery performance or public health management performance. And this insights gained can be used to recommend actions or guide decision-making processes. Data analytics can be performed over a health record or the health record data store for an individual patient or an individual healthcare worker. It can be performed on a patient, on a group of patient or cohorts, which might be based on a combination of demographic and clinical criteria. Analytics can be performed over enterprise groups based on specific healthcare teams, wards, clinics, institutions. It can also be done over geographical groups, which might be based on local area, a town, a region, or a particular country. The substrate is the data being analyzed. So every time we talk about a substrate, that is what we do our analytics over. And substrates for clinical data analytics range from unstructured free text, such as clinical notes or letters that you want to analyze. It can be structured documents, such as a discharge summary, which might use either SNOMED CT or other code systems. And then big data, which can include a combination of both structured and unstructured data. This diagram here summarizes the three main purposes of analytics over patient data. So firstly, we have clinical assessments and treatment, which benefit individual patients and clinicians. And then the data collected for the at a patient level for the individual patients can be grouped together for population health to benefit larger groups of people. And finally, we have evidence-based clinical research, which can in turn lead to improvements in treatments for individual patients. So we have this circle here that starts with the clinical assessment and treatment and then feedback to them in the end, but only because we would be able to aggregate and analyze and share our data. So when you talk about analytics, it may be specific from where you come from, whether you are thinking about it from a research perspective, population health, or for the individual patients. But think about it, SNOMED CT is actually designed to support all of this cycle, each of these different specific purposes. But how is it that the design of SNOMED CT can help us to support analytics? Maybe a bit of repetition, but I'll do it very brief. We have these concepts that represent clinical meanings, and they allow us to create queries that are based on the meaning of things rather than just words that we use to describe them. So the formal definition and the unique concept identifiers are very important for querying. The descriptions will help us to search for concepts, supporting multiple different ways of referring to a concept. And this can enhance the string matching that we may use in natural language processing tools. It can also provide multilingual support for queries through translations. Then we have the relationships, and they support queries where we use the definition of concepts. So where we not only rely on the concept identifiers, but where we actually use the defining characteristics for creating queries that require aggregations to be based on the meaning of the codes, and queries over the detailed content stored in our electronic health records. We have additional features as well. So the concept descriptions relationships you have already heard about, but we also have the concept model, which is it's a set of rules for defining and querying clinical meanings. Liara also spoke to this. So, and it also relates to what we discussed before with post-coordination. In order to create meaningful clinical representations of data, you need to use the concept model so that you don't start to say that that this is a clinical finding with a procedure side on the head, because a clinical finding can have a procedure side. So the concept model really specified the rules. Then we also have a set of computable languages, such as the compositional grammar, which was what we used to create an expression. But we also have the expression constraint language, which is used for querying. And we have templates for defining patterns of expressions or queries. Then we have reference sets, and we have spoken about reference sets in the context of translations, where we have a language reference sets. We have also talked about reference sets in the context of maps, where we have a reference set to represent maps, but it may also be that we use it to represent a subset or other ways. Finally, we have description logic, which provides the formal foundation for SNOMED, and that helps support computational reasoning. And that is an incredible, powerful design feature for data analytics. But as we also talked about in relation to post-coordination, description logic comes with SNOMED CT, because SNOMED CT has been reasoned and classified before distributed to members. But if you're doing things on your own, you also need to have that ability in-house to do sophisticated analytics. SNOMED CT's broad domain coverage also allows us to query across different disciplines, specialties, and clinical areas. We have a robust versioning mechanism built into SNOMED CT, and that will help us to manage queries over health records collected over a period of time. Recall how I showed you inactive concepts. They can still be looked up in the same way they can be queried. So even though we have concepts being inactivated and things are added, we can still go back and do analytics over historical data. SNOMED International is, or SNOMED CT is an international terminology to support data sharing and queries over international data sets. But we also have localization mechanisms to support more locally specific queries. So what you've heard about here is all the background. What is it that what is the mechanics? What is it that we can use to create data analytics features in our systems when we use SNOMED CT? So this was just a background. It's our toolbox, you can say. So now I want to talk about the specific techniques. So before you start using SNOMED CT for data analytics, you first need to make sure that your clinical data is coded using SNOMED CT. So if your electronic health record system records SNOMED CT natively in the records, then you can get started straight away. But if your patient records use other code systems or free text, then you first need to map or encode that data with SNOMED CT. So this was the implementation approach I talked about before, about indexing, using SNOMED as an indexing system. So SNOMED is often used as a common reference terminology to integrate and standardize data that use different code systems. Once you have your clinical data coded using SNOMED CT, there are a number of different techniques that you can use to perform data analytics, ranging from very simple to very advanced. The simplest approach is to compare each code that you have stored in your patient record to see if it's a member of a particular subset that you've designed specifically for your query use case. But you can also use subsumption to check if a code is a subtype of a particular clinical meaning, or you can use the concepts defining relationships to match against some query criteria. You may also use expression constraints, and you can use SNOMED CT's description logic for even more powerful reasoning. I'm now going to take you through the principles of each of these techniques. As I said, using subsets is the most simple way to do analytics with SNOMED CT. For example, you may want to find all patients with some tuberculosis disorder. And to do this, you can create a set of tuberculosis disorder concepts that you want to look for in the patient records. It may be that it's some very specific concepts or diagnosis that you want to identify. So you create this set of SNOMED CT concepts, and you can then scan through the patient records, looking at the diagnosis recorded for each patient. So here you have an example of a patient which have been diagnosed with this concept. So comparing that diagnosis code to the subset will show you that, yes, this patient has a tuberculosis of spinal meninges. So this patient matches the query. The next technique is subsumption, and subsumption is when one concept is a subtype of another concept. Because we have this polyhierarchical structure of in the SNOMED CT hierarchies that Liara already told you about, we can use these hierarchies efficiently to do analytics. So this approach uses the hierarchy, and let's just consider a small population here of people. Please note that we have omitted some of the concepts. If you go into the browser and explore all the supertypes of pneumonia, you'll see that there are many more. But essentially, it is a disorder of respiratory system and a type of disease. So there may be many more intermediate concepts in the reality. So we are looking at this population of people who each have one of these 4 types of disorders coded using SNOMED CT: viral pneumonia, bacterial pneumonia, tuberculosis of respiratory system, and suppurative otitis media. So these disorder concepts are organized within this hierarchy. So suppose you want to identify who within our population have a respiratory disease. This means that we have to identify all the descendants of the concept disorder of respiratory system, and then count how many people within our population is associated with any of the descendants. So here we use the relationships in SNOMED CT, or the hierarchical relationships that we call ISA relationships, to identify who within our cohort has a disorder of the respiratory system. And as we also talked about before, this is one of the key differences between SNOMED CT and ICD, because in ICD-10 we only have one category for all codes. So now we would either be able to identify it as a respiratory disease or an infectious disease, but with SNOMED we can do both types of queries. And with SNOMED, if we want to identify people with a bacterial infection, we would need to do the same, but with a different starting point. So now we want to find all the descendants of bacterial infectious disease. And then we can find all of those. So as you can see, some people fall within both of these queries. So when you do use SNOMED for counting, you need a way to ensure that you don't double count people, right? So it depends on what you want to do with your queries, because some will fall into both categories of your queries. So that is one of the things that you need to bear in mind when you count based on SNOMED CT. The last example is that we search for people with pneumonia. So this is just to show you that it's easy to use the hierarchies in SNOMED CT to group together patient records with different levels of granularity and different perspectives, depending on what information you're looking for. So the next technique is using the defining relationships to create the queries. And this involves filtering concept codes that we're looking for based on the value of that concept's relationships. So here you have an example of the concept infective pneumonia. You see it here. And this concept has three relationships. Infective pneumonia is a type of infection. And infective pneumonia is also a type of respiratory disease. Infective pneumonia has a finding site of lung. So we can use any of these concepts as an entry point or a predicate for our queries. Infective pneumonia also have a number of subtypes. One of these subtypes is viral pneumonia. And viral pneumonia has all the same relationships as the infective pneumonia because it's a subtype. It has the same definition, but there is something more specific about this. That is the characteristics of a subtype hierarchy, is that any subtype have the same properties as its parents or descent or ancestors. The same properties goes for this concept, but there's something making this concept more specific. So here you can see that this also have a causative agent of virus. So we might, for example, query our patient health records to find all the diagnosis code with a finding site that is a type of lung structure. And then you would match both infective pneumonia and viral pneumonia and any other disorder concepts that have a finding site of lung structure. So that will be matched over 1,000 of different codes. Here is a small example of how this would work. So in this example, we want to retrieve all disorders with a finding site of kidney. You see here we have 8 concepts, and we have just chosen to show you here the associated morphology and the finding site, because each of these concepts have these two defining relationships for them. So if we wanted to find all the disorders with the finding site of kidney, right, we would need to explore those relationships. And here in our data set, we would identify 3 concepts which all match on finding site kidney. And we may want to do a second query to match on those findings that have a benign tumor morphology. So we can use the other relationship to identify those concepts. And then if we combine those 2 queries together, we can find concepts which have both a morphology of benign neoplasm and a finding site of kidney, and then we would only find one concept. So it's like set theory. When you do this, you have these different types of characteristics, and then you specify in your queries what is the characteristics that we want to query on. And because we have not only a hierarchical structure in SNOMED, but a polyhierarchical structure and a very granular definition of our concepts, it gives us very many possibilities to do very selective retrieval and to really query data from the perspective that would be useful for the person doing the queries. We can define our query using the next technique, and that is to use expression constraints or the expression constraint language, which is shortened ECL. ECL is a formal syntax that allows us to query SNOMED CT to find a matching set of concepts or expressions. It uses a single less than sign, as you have it here, to represent subtypes or descendants of a concept. If you have 2 consecutive single less than sign, it takes all the subtypes, including the concept itself. So up here, we would only have all the subtypes of clinical finding. But if it had been 2 single less than sign, we would have all the subtypes plus the concept itself. So that is how, that's just a brief introduction to expression constraints here. So what this expression constraint does is to find all the descendants of a clinical finding with an associated morphology that is equal to benign neoplasm or any subtypes of benign neoplasm, and having a finding site of kidney structure or any type of kidney structure. So this is how we would express a query using the expression constraint language. And if we run this expression constraint over a substrate, it would be, I ran this yesterday on the February 2022 international release. We find that we have 24 concepts matching these criteria. You can see this two consecutive single less than signs here after the equal sign is quite important, because if we didn't have them, we will search for associated morphology equal to exactly this concept. But because we also want to have more refined concepts included in our query, we need to match on also the subtypes for both of these values. We're now going to use this expression constraint query we created before to analyze patient data. So we're going to look for those patients in our electronic health record that where the diagnosis is a benign neoplasm of the kidney. So here's an excerpt from the expansion of our expression constraint. And if we use this expansion and step through our patient record one at a time to check if their diagnosis is in the ECL expansion. So you can see this is similar to the approach we started out with the subset. Now we have just created our subset using an expression constraint. So that's an automatic way of creating a subset, you can say. And then the principle is the same. We go through and compare the diagnosis codes for our patients to the members of our expansion. And I can already warn you that now I'm going to say something with a very bad pronunciation, because here you can see that this patient, number 2, has a hemangioperitocytoma of kidney. And patient number 6 also matches. It has a benign tumor of pelvic ureteric junction. And if some of you are clinicians, you can correct me, please. I'm happy to do that. But again, patient number 7 here matches also on a diagnosis code that is found also in the expansion. And it's a juxtaglomerular, I can't pronounce it, but it's this disorder here, some form of tumor. I did actually yesterday try to sit and pronounce it, but you know, that was yesterday. The last one here also matches, as I said, in the concept, benign papilloma of renal pelvis. So you can see in our patient records, we can now identify 4 patients that would fall into this group of clinical findings with an associated morphology of benign neoplasm or a finding site of the kidney structure or any of the descendants hereof. The last technique in our list here of techniques is to use description logic. So using the logical foundation of SNOMED CT. So this description logic work is usually already done for you when you pick up a new edition of SNOMED CT, because before distributing a new release, we have classified SNOMED CT using a description logic reasoner. And this classification process generates all the new inferences from the stated definitions that the authors created. So that means that when authors of SNOMED CT define this is the correct properties for concept, they put this in, they represent these as stated relationships. Then we run SNOMED CT through this description logic reasoner, and we end up with these inferred relationships that ensures that a concept have all the appropriate subtypes and all the appropriate supertypes, and that the defining characteristics corresponds to the characteristics of their supertypes. So that description logic reasoning or classification process is super important for SNOMED CT, and that is really also what enables us to manage and maintain a terminology of the size that SNOMED CT has. That's because we have these tools and services that can really help us, combined with the very skilled group of authors. But there are some cases. So when you get a SNOMED CT release, you get the benefits of having this classified terminology, and you also get the benefit of the description logic whenever you use the inferred relationships in the relationship file. But there are some cases where you want to add new content that hasn't already been classified, and that is when you use it as an extensible foundation. If you create post-coordinated expressions, if you create new concepts, then you need a description logic reasoner to classify those post-coordinated expressions or concepts together with the entire SNOMED CT to make sure that you know where those expressions or concepts sits in the SNOMED CT hierarchy. And that is important then. If you have that feature, then you can go and do all the same types of selective analysis and sophisticated analytics features that you have just seen here using the other techniques. There's a range of reasoners, description logic reasoners available. So the description logic we use is not something specific for SNOMED CT. Description logic is generally applicable. You can use description logic to create a terminology of foods or cars or whatever domain you would want to create a terminology over. So description logic is a general technique. So there are many openly available or freely available reasoners, including FACT++, ELK, Snow Rocket, and there's a number of OWL query languages such as SparkQL and DL Query. And if you want to learn more about description logics, we have some presentations on the logical profile of SNOMED CT, where you can learn about the features of the SNOMED CT's logical profile. We also have presentations, recorded presentations on this. And you can read more about them there in these two links you see on this slide. Next, I want to talk to the analytics tasks, just keeping an eye on the clock here. There are three broad categories of data analytics tasks that I've showed you earlier. And here's just a few examples of the kinds of things you would want to do within each of these categories. For clinical assessment and treatment, SNOMED CT would be used to generate summaries of patients' clinical history, or to generate point-of-care reports for reminders or identifying care gaps, or reporting to disease registers, things like that. It could also be for clinical decision support, where you provide alerts, diagnostic support, or links to clinical guidelines. I'm going to show you some examples of this very brief shortly. For population health, SNOMED CT is used to perform trend analysis. And this could be to detect the incidence or prevalence of a disease or treatment. It could also be to predict the demand or to effectively allocate healthcare resources. You can use it for pharmacovigilance, where you want to monitor adverse effects of medication products. Or you can use it for clinical audits to improve patient care. And this would be done by reviewing the care that's delivered against defined standards. You can also use it for clinical research, where you would use SNOMED CT to help identify clinical trial candidates, or to predict the probability of a disease, or for other research tasks. It could be semantic searching over medical literature, where you have tagged the literature with SNOMED CT codes. I just want to show you some examples of some of these tasks. This is an example of a clinical decision support put into practice in a medication setting. So here you can imagine we have this patient, John Smith. He has been diagnosed with pneumonia. So a clinician is just about to prescribe a new drug, in this case, amoxicillin 500 milligram tablet, which is a product that is associated with the concept in SNOMED CT. However, upon prescribing this drug, we have a clinical decision support rule built into this system, checking this input field to see, comparing what is selected to the past history or any allergies recorded for this patient. So this clinical decision support rule checks if there is an occurrence of penicillin allergy. And in this case, John Smith does have a penicillin allergy. So an alert is displayed to remind the clinician of this allergy. And maybe there is some mechanism to search for safe alternatives. And safe alternatives could be represented by SNOMED CT concepts, where you have put it into a value set of codes that are used as alternatives to penicillin. You can create a small terminology value set for that. So SNOMED CT can actually help to implement such description support or decision support logic as we have just seen here. So to do this, we're leveraging the SNOMED CT drugs concept model. As the patient is allergic to penicillin, we need to check the prescribed item to see if they contain a substance that is penicillin. We can express the test as a SNOMED CT expression constraint, as you have it here. So any pharmaceutical biological product which has a precise active ingredient, some kind of penicillin or penicillin itself. The drug model of the product that we selected, amoxicillin 500 milligram oral tablet, has a precise active ingredient of amoxicillin. So the substance model tells us that the substance, amoxicillin, is a type of penicillin. So if we look up amoxicillin, you can see that that's a type of penicillin. So like in my previous presentation where we looked at the comparing hospital A, B, and C, we use that for interoperability, but here we use the defining relationships for decision support because we have the value of the has precise active ingredient is amoxicillin, and that is defined as a subtype of penicillin. So the alert should be triggered when you have this match. And it may seem like a trivial example, but the same approach can be applied where the pharmaceutical biologic product name does not immediately tell us the name of the substance that it contains, because the SNOMED CT model holds this information. We can also use it to link to patient records to relevant clinical guidelines. So imagine that you have a patient that has been diagnosed with something, and the clinician will then get a pop-up with a clinical guideline telling how they should, how the appropriate process for treating this patient would be. So SNOMED CT concepts can be applied as a semantic metadata tag to these clinical guidelines to specify the clinical codes that indicate the need for this guideline. So here you see this guideline may be relevant for any diagnosis of asthma, or when an asthma management regime is put in place, or when an asthma control questionnaire is completed. So we can think of the clinical guideline as a document, with the document guidelines themselves being part of the body of the document, and then the concept identifiers appearing in the document header as metadata. So EHR systems, which are designed to use clinical guidelines marked up with semantic tags, as I just showed you, can display the relevant guidelines to the user when a user selects and records an appropriate or relevant concept in the health record. On this slide, we have a generic template that could be used in an electronic health record to facilitate the display of an appropriate clinical guideline. For example, this template could be used on a clinical guideline that has a semantic tag for asthma, generating the following clinical decision support rule. So if the diagnosis is asthma or any subtype of asthma, then display this asthma care quick reference. And that could be like a hyperlink or just a link to that document. So in practice, it would be that when a clinician records the concept, which is a subtype of asthma, so it's within this expansion, then the actual clinical guideline would be populated. So this approach enables contextually relevant clinical knowledge to be presented to the user based on specific codes recorded in the patient's health record. So SNOMED CT is not trying to make decisions, to make the clinical decisions. No, SNOMED CT tries to make the decision-making process easier and support accurate decisions to be made. it's part of the implementation to make it reflect what you would want in your implementation. I can see we only have a few minutes left, so I'm going just to briefly show you these slides, and I know you have the handout, so you can read through this afterwards. But expression constraints are these queries that we define using a specific syntax, and we use expression constraints to get an expansion of SNOMED CT concepts. So where you can create a set of concepts just using a single query. So every time you create a set of concepts that you want to use, you don't have to manually sit and select them. You can use it using a generalized query. And of course, when you run a query, it's important to know your substrate, what version or what edition of SNOMED CT you are using, because that will affect the expansion or the result of the query. And you can use expression constraint not only for analytics, you can use it for terminology binding. When I showed you the user interface before the break, when I said that this data entry field is bound to a specific set of SNOMED CT concepts, the disorder field were bound to all the sets of diseases. The procedure field could be bound to all sets of procedures. So that's how you would use it for terminology binding and intentional value set definitions. And as I've just showed you here, we can use it for queries, and we actually also use it to specify rules for how you can post-coordinate or create new concepts. There is a certain structure. It has focus concepts. There is a constraint operator. You can use it to reference as member of a specific reference set. You can use conjunction, disjunction. You can have a refinement, which uses the attribute relationships. So you have attributes with both a target or a source and a type and a target. And you can also specify groups of relationships that you want to match against. And here you see an example of disjunction, which is also possible. So there's this diagram illustrates all the different parts that can be included in the expression constraint, in an expression constraint. And in this document here, you can read the details about how it's used and what it does. These are the symbols, and these are what the symbol does. And the next set of slides, the browser also have an ECL function, so you can go into the browser and run an expression constraints. This is how the user interface look. You enter the expression constraint and click execute, and the result is populated in the bottom. In this last set of slides, there is a set of examples where you want, and you can read what it does. Descendants of fracture of femur is like this. Descendants of self is done like this. And then if you go and try it out in the browser, you can try to apply your other concept ideas than fracture of femur. But this list here will tell you what syntax to use. And similarly, in the following slide, we have examples of conjunction, disjunction, and exclusions with an explanation of what it does. These examples and more examples are also to be found in the expression constraint guide. So here we have where we execute or where we run an expression constraint over sets of attributes. And we also have cardinality if you want to look for concepts with more than one finding site relationships, or with less than 3, or with precisely 3 active ingredients. There are different things that you you would want to query. And then there's also reverse flags and dot notations, which are a bit more advanced features in the expression constraint language, but you can look at the examples here. Up here, we would use the reverse flag to find the precise active ingredients for any calcium-containing product. So in this case, we use the attribute relationships in reverse. So the last part here about what the expression constraints syntax is about. I could have spoken a lot more about that, but I hope there will be an opportunity later for you to dive into the details of the expression constraint language, because it is really a powerful language and it's used very effectively in SNOMED CT implementations.